Assam alaikum everyone, welcome back to Modern Study Pro. Hope you all are fine. In today's video, we are going to announce our new series of chemistry, practical-based assessments. In this series, we will complete all the experiments of chemistry that are given in your federal board syllabus. Hope this will help you.
All right, let's jump right into something that sounds, well, basically impossible. Taking a liquid that's been perfectly mixed, like alcohol and water, and just pulling it apart again. Today, we are going to break down the amazing science behind fractional distillation. I mean, really, think about it. You stir them up, and they look like one single totally clear liquid. You can't just filter them, right? And you can't skim one off the top, so how in the world do you do it? Well, it turns out the secret isn't about how they look, it's all about how they act when things get a little heated. So, here's how we're going to tackle this. First, we'll lay out the puzzle itself. Then we'll dive into what I like to call the boiling point race. That's the key to the whole thing. We'll meet the star of the show, the fractionating column, see a step-by-step of the experiment, and then we'll connect it all back to why this is so important in the real world. Okay, so here's our challenge. We have what scientists call miscible liquids. And really, that's just a fancy way of saying they mix together completely, like ethyl alcohol and water. Our mission, should we choose to accept it, is to get pure alcohol out of this mix and then have pure water left over. And the tool we're going to use for this mission is called fractional distillation. Now, the core idea here isn't some kind of crazy complex chemistry. It's actually all about physics. The entire process hinges on one simple, elegant fact. Different liquids boil at different temperatures. That's it. Yeah, I love thinking about it like a race. The liquid with the lower boiling point, that's our sprinter. When we start applying heat, it's the first one to burst off the starting line, break free from being a liquid, and turn into a vapor, leaving the other one behind in the dust. And here are our two runners. On one side, you've got ethyl alcohol. It boils at a pretty brisk 78 degrees Celsius. On the other side is water, which waits all the way until a full 100 degrees Celsius. That 22-degree difference, that gap, that is everything. It's the whole reason any of this works.
So let's just lock in on that number, 78 degrees Celsius. This is our target temperature. This is our magic number. If we can carefully heat our mixture and just hold it right around this point, the alcohol will start turning into a vapor, while the water, for the most part, just stays behind as a liquid.
But here's the thing, just boiling isn't quite enough to get a perfectly clean separation. We need a special piece of equipment to really nail it. And this is the real hero of the story. It's called the fractionating column. So just picture this. The alcohol vapor, maybe with a little bit of water vapor tagging along, starts rising up out of the boiling flask. As it enters the cooler fractionating column, which is often full of glass beads or rings, it cools down just enough to condense back into a liquid on all those little surfaces. But here is where the genius comes in. The heat still rising from below immediately re-vaporizes that liquid. And because alcohol boils more easily, this new vapor is now slightly richer in alcohol than the liquid it just came from. This little cycle of condensing and re-vaporizing happens over and over and over again, all the way up the column. By the time any vapor manages to get to the very top, it's almost pure alcohol.
So, let's meet the whole team. You've got your flask to hold the mixture, the all-important fractionating column to do the purification, a thermometer to watch that temperature, a condenser to turn our pure vapor back into a liquid, and a receiving flask to catch our final product. And of course, a heat source. All right, theory is great, but let's walk through how this would actually go down in a lab. We're going to follow a simplified guide just to see the science in action. Okay, first, you get everything set up and add your mixture to the flask. Next, and this is critical, you place the thermometer so the bulb is measuring the temperature of the vapor right before it heads over to be cooled. Then, you heat gently. As that thermometer hits 78 degrees, you start collecting what comes out. That's going to be your alcohol. Now, as soon as you see the temperature start to climb past 78, you got to be quick and swap out that flask. That's your signal that the water is starting to boil. Now, this whole thing isn't just some cool lab trick. This process is a massive, massive cornerstone of modern industry. And when you understand it, you start to see how so many products we use every single day are actually made. Let's look at a few examples. The single biggest use, refining crude oil. Crude oil is just this complex soup of hundreds of different things. Fractional distillation is literally how we separate it into gasoline, kerosene, diesel fuel, and everything else. It's also, of course, used for purifying alcohol for beverages or medical uses, and for countless other chemical separations in industry. Okay, so if you were ever going to do this, there are some vital rules. You have to heat gently and continuously. We already talked about how critical that thermometer placement is. And you've got to make sure your joints are sealed. Otherwise, all that valuable vapor just escapes into the room. But there is one precaution that is more important than all the others combined. And this is the big one. You must never, ever create a completely closed system. When you heat a liquid, it expands and creates pressure. If that pressure has nowhere to go, your glassware effectively becomes a bomb. It will explode. The system has to be open to the atmosphere at the very end to be safe. Period.
So we've seen how fractional distillation is used for fuel and alcohol, but where else might this super fundamental process be hiding in plain sight? Think about perfumes or essential oils. The applications are just vast. What do you think? Pretty cool when you start to look for it. Thanks for watching.